you, sir. Now the next session will be on the subject Convergence in the Philosophy of Mathematics, and that talk will be given by Dr. Edward L. Zalta, Senior Research Scholar, Stanford University. So before we start, I'd like to speak some lines about him. Dr. Edward L. Zalta is a Senior Research Scholar at the Center for the Study of Language and Information. His research specialties include metaphysics and epistemology, philosophy of mathematics, philosophy of logic, and computational metaphysics. Dr. Zalta has published 2 books. One is Abstract Objects, an Introduction to Axiomatic Metaphysics, and the second one is Intentional Logic and the Metaphysics of Intentionality, as well as the articles in the Journal of Philosophy, Journal of Physiological Logic, Journal of Logic and Computation, Bulletin of Symbolic Logic, and among others. Dr. Zalta has taught courses and faculty seminars at Stanford University, Rice University, the University of Salzburg, University of Auckland, University of Tasmania, University of Padua, University of Santiago de Compostela, and Ludwig Maximilians University, München, Munich Center for Mathematical Philosophy, and has lectured in various universities in the United States, Canada, New Zealand, Australia, Great Britain, Germany, Australia, the Netherlands, France, Italy, Spain, Poland, Slovenia, Peru, Brazil, Israel, China, and Japan. His other philosophical interests include modern logic, formal semantics, contemporary analytic physiology, contemporary history of philosophy and modern philosophy, etc. Dr. Zalta is also the principal editor of the Stanford Encyclopedia of Philosophy. So let's go on the talk over Convergence in the Philosophy of Mathematics, and enjoy. Thank you.
Testing. You need me to test? Okay, we're good. Thank you. Well, thank you very much for that kind introduction. Today, and again, I'm very grateful for being invited to this conference. I'm going to try to give you a theory today of how to understand mathematical theories, no matter whether they're mathematical theories in the past, in the present, or in the future. I'll give you a formalism for trying to understand that, and that's how I will try to unify various philosophies in mathematics. Okay, so let me set up my question as follows. I'm going to suppose that logic provides a setting for mathematics, that without some principles of reasoning, mathematics is not possible. So logic is going to be in my background. But of course, some mathematicians, Boole and Frege and Church, give mathematical treatments of logic. But I'm not going to follow them in that regard. I'm not going to presuppose any mathematics. I'm going to follow Russell and Whitehead, who in Principia Mathematica from 1910 started with relations and predication and reduced sets and functions in terms of relations. So that's where my background is going to be. Now, to show you the power of that, let me note that the logicians suppose that an atomic statement has some logical form. X stands in relation R to Y. They write it this way with infix notation, or this way with the relation term at the beginning of the expression. And now they can unify not only ordinary language, language about two individuals, John loves Mary. But language about mythical characters like Jupiter, Caesar worshiped Jupiter, and 1 is less than 2, and 0 is a member of the unit set. The null set is a member of the unit set of the null set. All of those 4 sentences have the same logical form. Right? So logic allows us to draw inferences in exactly the same way from all 4 sentences. So logic provides a kind of unified background framework that I'm going to presuppose for this talk. And in each of these cases, the names like John, Mary, Caesar, Jupiter, 1, 2, the null set, and the unit set of the null set, they denote individuals. Whereas these expressions, loves, worshipped, is less than, and is a member of, those denote relations. In this case, it's 2-place relations. But there can be 3-place relations as you learn X gives Y to Z, and there can be 1-place relations, which are just properties, like being happy, being prime, things of that kind. So logic is where my background starts. And then my question is, what do terms like 1 and 2 and the null set and the unit set of the null set, what do those terms denote? What things do we have to postulate in order to understand them? And my answer is going to be, they all denote abstract objects. And the thing to do as a metaphysician is to systematize the domain of abstract objects and show that the mathematical objects form one small subdomain of the domain of all the possible abstract objects. And that will unify various philosophies of mathematics. How is that going to happen? Well, the philosophy of mathematics is divided up into many different opinions. I'm going to show you now at least 8 or 9, possibly 10 opinions about what mathematics is. They try to give the answer to the question, what are those things that mathematicians talk about? There's the answer called Platonism. By Plato and Gödel, they thought that mathematics is in an independent reality that transcends nature. It's outside of the causal order. And Gödel believed in this form of this Platonism. Then there's the logicists. The logicists like Frege and Whitehead and Russell, they thought, well, mathematics is not something really independent. It's really reducible to just pure principles of logic, which we can know just by their meaning alone. And logical principles are supposed to be analytic and known a priori. And so they tried to reduce all of mathematics to logic. There's another, and that's very different from Platonism. And then there's another version of philosophy of mathematics called structuralism, which you get from, that goes back to Dedekind. Dedekind thought that there were all of these simply infinite systems of numbers, right? And he said their only properties were the other relational properties that they bear to this other members of this simply infinite system. And in recent times, that's been defended by Benaceref, Shapiro, and Resnick. Then there's something called inferentialism. Mathematics is not structures, it's simply the inferential role of the terms. We somehow objectify the inferential role. And that's something that Wittgenstein gave us, and Wilfrid Sellers and Robert Brandom. They all think that mathematical language is really just capturing, making explicit the inferential role of these terms, like the numeral 1 and the numeral and the membership relation. Then there's people who are like Hilary Putnam and Jeffrey Hellman, who think that, well, those simple atomic statements, 1 is less than 2, those aren't what's really mathematics is about. Mathematics is about conditionals of the form, if all the axioms of piano arithmetic are true, then 1 is less than 2. That's how you're supposed to interpret the statement 1 is less than 2, not as an atomic truth, but as the consequent of a conditional, the antecedent of which is the conjunction of all the axioms. That's very different from the ones that went on before. Then there's formalism. Hilbert and Curry, they think that mathematics is just a game played with formal symbols. And then there's naturalism. Quine. Quine thinks that the principles of set theory and mathematics generally are really part of natural science. They can be revised in principle, but they typically aren't revised because they stand at the core of our web of beliefs. And when we revise things because of recalcitrant data, we typically revise the physical theories before we revise the mathematics. But Quine says the principles of set theory are just like principles of physics. That's a little strange to me, but that is a position in the philosophy of mathematics. And then there's fictionalism. Fictionalism has been defended by Hartree Field and Goodman, which is also a kind of nominalism, which says those terms in mathematical theories, they don't denote anything really. Or if they denote fictions, whatever those are. And that's what fictionalism is. And finally, there's Carnapianism. Carnap thought that, any mathematical framework has about its own group of objects. And so he was very liberal in accepting all these different frameworks because he distinguished between do they exist as an external question and do they exist as an internal question. Internal to the theory, of course they exist. But external to the theory, he says the existence question is just a practical matter. So these are a lot of different philosophies of mathematics, and they're not compatible with one another, really. They don't look compatible. Now, I've left out some, and I may have left out your favorite ones, but I'll tell you why I've left them out. I've left out psychologism, because that's the theory that numbers and other mathematical objects are just ideas in the mind. I don't really I'm not going to talk about that because Frege had a devastating critique of that. And I've put aside intuitionism, constructivism, and finitism, not because they're not good theories. They're very, very good theories, but what they do is something different. They also advise and say to mathematicians, you should practice mathematics in a certain way. I don't want to tell the mathematicians how to practice. The intuitionists and the constructivists and the finitists say you should use only a certain set of tools, possibly a certain limited set of logical tools. I want to leave the mathematicians free to go to do whatever they want in developing mathematics. So I put those aside. Now, in the rest of my talk, I'm going to follow Stuart Shapiro's distinction between three kinds of foundational questions. There's metaphysical foundational questions, epistemological foundational questions, and mathematical foundational questions. I'm not going to be interested in mathematical foundations. That's for the mathematicians to decide. They may decide there's one mathematical theory to which every other mathematical theory could be reduced. It might be set theory, ZFC, plus some large cardinal axioms. It might be category theory. It might be homotopy type theory. That's a matter for the mathematicians to decide. And the reason is because once they decide, they may decide, yes, there is one foundational mathematical theory. My question then applies to that. What does the terms of that foundational mathematical theory mean? What do they refer to? And if the mathematician says there's no foundational theory, well, then my question applies to all the different mathematical theories. So in any case, I'm not going to be talking about mathematical foundations, only the metaphysical foundations and the questions about how can we know and get access to mathematical objects. So now, given that distinction, how do we decide among all those different alternatives that I gave you before? There's a problem that even confronts the people with all these different views, and some of them can't even agree on what the data is. Platonists think that 2 + 2 = 4 is just true, whereas the fictionalists say, oh no, that's false. That's like Pegasus has wings, or Zeus lives on Mount Olympus. Those aren't really true. They're only true in a story. Whereas Platonists say 2 + 2 = 4, that's just plainly true, not relative to any story. I'm going to show that there's two sides to this question, and that both of them are pointing to something that's right, but right now, most philosophers of mathematics can't explain why there's even disagreement about this question. So that's going to be an important thing. So we need an explanation as to why there are even divergent views about this data. And that's what a successful philosophy of mathematics should do. So now the final group of issues that I want to talk about is that if you look at the history of mathematics, starting, of axiomatic systems, going back to Euclid, the mathematicians have been using principles in the attempt to characterize entities whose only properties are the mathematical properties given by the principles. Now the problem is, with using modern logic, classical logic, there are no objects. There are no objects whose only properties are mathematical properties. Why? Well, because classical logic requires that for every object x and for every property f, either x has f or x doesn't have f. Or put it this way, where f bar is the negation of f, it requires that every object and every property is such that either x has f or x has its negation. Well, you might argue, let's revise classical logic, but I think there's a way of preserving classical logic, which makes a lot of sense to me, and that's what I'm going to be supposing. So I'm going to try to find a solution to this problem. How can there be objects whose only properties are their mathematical properties? Now, the logicians think that there's a formal solution to this problem. What they do is they formulate a mathematical theory in a language that's very restricted in its expressive power. So, for example, they formulate the Peano number theory with just the symbol 0 and the successor function, the prime symbol, and then they say, so look, I've got objects and their only properties are the ones you can express in this language. But that's a kind of cheat. I mean, Russell saw through that already in criticizing Dedekind when he said, look, it's impossible that the ordinal should be, as Dedekind suggests, nothing but the terms of some relations as constitute a progression. Because if they're anything at all, they have to be intrinsically something. That is, they've got to be intrinsically, for every property, they've got to have either that property or its negation. Otherwise, they're not really objects. So, of course, one could revise number theory to include this predicate is a number, and 0 is a number as an axiom, and add that as an antecedent to all the axioms. But that's not a very successful story, because here's the question. Consider Zermelo's set theory. That's Z. That's this notion Z, Zermelo's set theory. Now, you can formulate Frankel's replacement axiom. What happened? Good. You can formulate Frankel's replacement axiom in Z. But then the question is, in the theory Z, just Zermelo's axiom without replacement, you can ask the question, does the null set in Z denote a set such that replacement is true, or one such that replacement is false? Again, similarly, the continuum hypothesis is formulable in ZF. So does the null set symbol, that symbol there in ZF, denote a set such that the continuum hypothesis is true, or such that it's false? So there's a kind of mathematical incompleteness. Of course, mathematicians can't really define objects that are determinate with respect to every property whatsoever. And you might ask, how can there even be such completeness among mathematical objects? So what I'm going to then do is show you that there's a sense in which mathematical objects have properties in two different ways. Their internal properties are incomplete because they're just given by the theory, whereas their external properties like being abstract and not having a length and not being colored, I mean, the number 1 doesn't have a color, but that's not given by the axioms. So I'm going to argue that that's a property that is exemplified by mathematical theories. And so we'll be able to ask which properties of mathematical objects are the ones that they have necessarily. And we'll be able to address an additional worry to distinguish the numbers that Frege gave us from the numbers that Peano gave us. There are many different kinds of number theories. So that's how we're going to do it. The final issues concern the epistemological foundations. How do you refer and have knowledge of things that are not in space and time? Right? We're finite beings, we have consciousness, but there's no light traveling from numbers to my brain. There's no information pathway from the numbers into my mind. So how is it that I can have knowledge and refer to objects, right? All of these philosophies of mathematics have this issue. The fictionalists and the nominalists think, well, I don't even believe in them as existing, so I get a free pass. But they don't. They don't really get a free pass. They have to give you an answer as to why it is that mathematicians think they have knowledge, mathematical knowledge. And so these epistemological problems are really serious problems for many of these other kinds of philosophies of mathematics. So I'm going to be operating under the following constraint, namely that a view of mathematics requires that we shouldn't postulate a transcendent reality that we can't access in order to get knowledge of those things. Because otherwise, mathematics will then just essentially be mysterious. I want to try to give an analysis of mathematics so that it becomes something that we know humans can engage in as a practice and do it successfully. Because if you think it's just a purely mystical thing that you can't access, then you wonder, why are we doing it so successfully? Right? That's a problem. So I'm going to try to give answers to these epistemological questions that arise straightforwardly from the metaphysics. Okay. All right, now here's my quick outline, and then we're going to do something technical and give you a technical understanding of the solution. I'm going to produce a single logical formalism and use it to analyze arbitrary theories in mathematics. You'll see how. And then I'll show that this formalism has multiple philosophical interpretations. On one interpretation, it's Platonism. On another interpretation, it's logicism. On a third interpretation, it's structuralism or inferentialism. And you'll see that it captures, and I won't be able to go through the entire list in a short talk, but I will give you some idea of how that's going to work. So, and I will explain that there's disagreement about the data by giving a reading of mathematical statements on which every mathematical statement ends up having a true reading and a false reading. And that will explain why there's disagreement. And then the Platonists focus on the true reading, the fictionalists focus on the false reading. And then I'm going to try to explain why their theory should explain the sense in which the only properties that a mathematical object has are its mathematical properties. The Platonists focus on the false reading. And then I'm going to try to explain why their theory should explain will emerge. And then the only properties that a mathematical object has are its mathematical properties. Okay, so now I'm going to give you the theoretical part. The theoretical part is technical, but it requires you, if you know already one course in logic, then the rest of this should be easy, because I'm going to add just one new technical notion in order to make all this work. I'm going to suggest that abstract objects, and basically what I'm thinking of as abstract objects are things that are not in the natural world, but nevertheless we need to postulate them in order to characterize our states of consciousness. We need a kind of background theory that will allow us to say, this state of consciousness is about the null set, this state of consciousness is about the number one of piano number theory, this state of consciousness is about the continuum hypothesis in ZF set theory. So I'm going to suppose that abstract objects generally, they're not given in nature, but rather they're defined by the way we conceive of them. So it's our conceptions. You have a favorite abstract object? I ask you, well, what are its properties? You have to tell me what its properties are. That's your conception of the abstract object in question. And you're free to develop various kinds of abstract objects. Mathematicians are free, and they can say, I've got a relation that's transitive, symmetric, and dense as an ordering. And, for example, then we might say that that's a mathematical theory. He could give a theory of, let's say, dense linear orderings by giving you properties of a certain relation. And so that holds for every mathematical object that you can conceive of. You have a favorite mathematical object, you have to tell me what its properties are. I'm going to say that those properties that define it are encoded by that object internally, but they're not exemplified by that object. They're not exemplified as opposed to encode. And I'm going to use the notion of encoding to define these internal properties. Now, this notion of encoding comes actually, and it's found in a work by an Austrian philosopher from 1912, and the way you formalize it is you introduce this notation, x to the left of f, whereas in standard logic, you also keep the standard notion of predication, x1 through xn exemplify the relation fn, right? So I'm going to build a formalism that extends classical logic with a new kind of predication and use that to give my theory. And you can find this distinction in other philosophers as well. Boulos and Kripke have versions of it, but it's not formal in their work. So, let me give you some examples. What is the Platonic form of the triangle? What is pure triangularity? The triangle, when we say the triangle has three sides, or the triangle has interior angles summing to 180 degrees. I'm not talking about a particular triangle. I'm not talking about a physical object. I'm talking about this Platonic ideal. And what that's going to end up being on my theory is it encodes all and only the properties that are necessarily implied by the property of being a triangle. So you take the property of being a triangle, it implies having three sides, having three interior angles, having interior angles summing to 180 degrees. You take all the properties implied by that, and it doesn't imply whether it's equilateral or whether it's isosceles. It just implies the things implied by being a triangle, and you build an object out of that. That's your conception of the triangle, and my system will then formalize that as a specific object in the domain. Similarly, the Dedekind piano number 1 is going to encode its mathematical properties that are given by the axioms of Dedekind piano number theory. So each abstract object is going to encode a unique group of properties, and the way I formalize this is I take a predicate for being abstract. This predicate here is the A with a bang with an exclamation point. And you read that X is abstract. And this backwards E with the exclamation point means there is a unique thing, X such that phi. So then I'm going to assert that for any properties satisfying, this is now a schema that has an infinite number of instances, depending on what formula you put here for phi. If phi is any formula that has a condition on this free variable f, then the result is a statement that's an axiom of the theory of abstract objects. It asserts there is an abstract object that encodes all and only those properties f that satisfy phi. Okay? So there's going to be, and in fact there's going to be a unique one because two abstract objects are going to be identical whenever they encode the same property. So that means that this definite description is canonical. It always has a denotation no matter what you put in for phi. There's always going to be a corresponding instance of comprehension that asserts that there's a unique such thing, right? So, we can skip the idea. There are paradoxes lurking, but I've taken steps to avoid paradoxes. So how is this kind of theory going to help us? Well, I'm going to have to move quickly now because I'm running out of time. Suppose the is of natural language predication is ambiguous between two kinds of predication. X is F means either X exemplifies F or X encodes F. Well, then if you take G necessarily implies F, this is how you express that in modal logic, then the form of the triangle becomes this. Remember, the form of the triangle is the abstract object that encodes all of those properties F that are necessarily implied by being a triangle. So you can write that down. And you can do that now for any property that a theory encodes. Right? So phi sub t is going to be the form of the triangle. Okay, so let me skip this and move on. So here's an example of piano. So now take piano number theory or piano arithmetic. What does the symbol, the numeral 1 symbol in piano arithmetic mean? Well, you basically say, you take all the theorems of piano arithmetic, look at all the properties of the number 1 in those theorems. All the properties, what are those properties? Being such that it's greater than 0, being such that it's less than 2, being such that it's not prime, it's the one before the first prime number, blah, blah, it's being such that it's odd. You take all those properties and you encode them into an object. that abstracts out an object that we can now say is what the numeral 1 means in piano arithmetic, okay? That allows us to distinguish the properties, excuse me, the properties that the number 1 encodes from the one it exemplifies. Now I can say the number 1 encodes only its mathematical properties. That's what this tells us. But it exemplifies not being red, not being colored, not having a shape. It exemplifies for every property either it or its negation. So it's complete with respect to the properties it exemplifies, but it's incomplete with respect to the properties it encodes because it only encodes mathematical properties, okay? So that's the general picture. You can supply, and I'll show you now quickly, you take any theory T, take your favorite mathematical theory T, and take the theorems of T, and whenever you've got an axiom or a theorem of theory T, you add to object theory this fact that T encodes being such that phi, where this symbol here is defined as T. Now the theory T itself is an abstract object because it's a body of content, it's a body of propositions, and it encodes the property being such that P, where P is a proposition here, and that way you can take as a reduction axiom the following principles. You can say, look, take any constant in T, 0 of piano number theory, the null set of ZF. Those are constants of T. And you can identify them with the properties that they have in their respective theories. So you get, as a consequence, that the constant in question encodes a property if and only if it exemplifies the property in T. Now this helps to really give us an interpretation. This formalism now works for an arbitrary mathematical theory. Now, each different way of interpreting the formalism gives us a precise way of understanding one of those philosophies of mathematics. Clearly, we've already got Platonism, and I'm going to skip this slide. So we've already got Platonism because the terms of mathematical theories denote abstract objects and relations. Platonism comes for free, so I'm going to skip that one. What about logicism? Well, logicism says mathematics is reducible to logic and analytic truths, but of course that doesn't work because logic is typically weak, whereas mathematical theories have very strong existence claims. So you might wonder, why was logicism ever a viable option? And in this case, the idea here is that object theory gives us a new kind of reduction. The terms and predicates of mathematical theories are given denotations because what those objects are that I postulated with that comprehension principle, they become logical objects. That is, they simply embody the freedom that we have in formulating conceptions of mathematical entities, or any kind of entity, by way of their properties. So this is a kind of capturing the logic underlying consciousness. We are free in our conscious thoughts to formulate any sort of theory about mathematical objects, and what that gives us is a kind of logical principle for generating objects to capture those states of consciousness that are about specific mathematical things. And I'm working on a paper now I'm working on a paper with others to try to make this more precise. Now, I'll quickly say that this gives us structuralism the way Dedekind wanted it, because Dedekind, remember, wanted objects whose only properties were their mathematical properties, and here we've got a reading for that. We've also, these special objects that encode and exemplify properties, they do encode only their mathematical properties. Of course, they exemplify properties as well, but that's okay. Dedekind simply said you need to have objects whose only properties were their mathematical ones, and that is captured. And this gives us readings for something that Paul Benacerraf said about, he said, in giving the properties of numbers, you merely characterize an abstract structure. And the distinction lies in the fact that the elements of the structure have no properties other than those relating them to other elements of the structure. And here we've got objects whose encoded properties are only the properties relating them to the other elements of the structure. So we get structuralism. Inferentialism. Remember, what I did was, I started with the principles, I took the axioms and theorems, and then I reduced them by turning the theorems with a single line into analytic truths of this form. And so no matter what mathematical object you're interested in, you can abstract its inferential role and turn it into an object. We're reifying the inferential role of each mathematical term. And that somehow is a way of, I think, is a way of understanding inferentialism as a theory. Formalism. What about formalism? Well, very quickly. The formalists say mathematics is a game by manipulating formal symbols. But what are symbols? Of course, if you want to talk about symbols, you have to invoke the type-token distinction. If I ask you, how many letters are printed on the next line? How many letters are on that line? Well, there's two possible answers. There's only one letter printed, namely the letter A, or you could say there are two letters printed, namely the letter A on the left and the letter A on the right. But a better solution is to say, look, there's one type of letter, the A, the letter type A, and there are two tokens of the letter A there. So when Hilbert and others talk about formalism, they're not talking about the tokens. Mathematics is not about physical inscriptions on the page. They're about types of things, mathematical symbol types. And those are abstract, and we have a way of understanding the type-token distinction. It's the types encode the properties that the tokens exemplify. Okay, finally, I'll move on to fictionalism. And fictionalism is basically, you get that for free by reinterpreting the quantifier. There is, this backwards E can be read there is, not there exists. Of course, Quine told us that we have to read it as there exists, but I don't think we have to do that. I think we can simply read it as there is without implying existence. And so you then get a reading on which these abstract objects are not possibly concrete things, but rather not the kind of thing that could exist. So the numbers become non-existent things. That's a kind of fictional view about mathematics. But you get that for free as an interpretation of the formalism by reinterpreting what the primitive terms in the formalism mean. Okay? So I'll skip that. So let me summarize. Last slide. Different philosophical interpretations of a formal framework and its analysis give us the different philosophies of mathematics. I gave you a formal framework. I showed you how it can describe abstract objects generally and how any arbitrary mathematical theory can be interpreted in that framework. But then we gave an interpretation of that framework, many different ones, and those captured the philosophies of mathematics. So that means that in many ways, all those different philosophies of mathematics become unified by a single formal framework. And that's the idea behind this talk. So this explains why the different philosophers of mathematics can't even agree on the data. Basically, the Platonists who think mathematics is true and the fictionalists who think it's false, they're looking basically at the same formalism in mind, but they have different interpretations of that formalism. And on one, the Platonists are focusing on the encoding readings, which are true, and the fictionalists are focusing on the exemplification readings, which are false. So this explains mathematical and metaphysical incompleteness, because the incompleteness comes on the encoding side, not on the exemplification side. And now we can explain knowledge, because knowledge all reduces to descriptions. Descriptions anchored in a theory. All you have to do to get into contact, get your mind into contact with an abstract object, is to understand its defining description. All of those objects that I identified earlier in the talk, they have a unique canonical description saying which object in that domain they are. So knowledge is by description, not by acquaintance. We don't need some special information pathway in order to access the numbers. And I didn't talk much about Carnap, so I'll skip the last bullet point. So let me stop there and say that that's how I want to present a unified way of thinking about the philosophy of mathematics, in which all these other different balkanized views about the philosophy of mathematics can all be grouped together using one formalism. Thank you very much. So there should be time for questions now.
Thank you so much, sir. Now the forum is open. You can ask any question what is in your mind right now.
Yes, I would like to ask a question. But first of all, this was a very, very interesting talk, and the subject was completely new to me, so I'm not going to ask any technical questions.
Sure.
But I think I interpret your talk in the right way when I say that you consider mathematics as a product of the human mind.
I don't know whether I go that far. I would say that whatever mathematics is, in order for us to understand it, we have to make our own conceptions of the things in question. It may turn out, so I didn't commit myself to any of those particular philosophies of mathematics.
I know.
There might be one that's distinguished, and so for all I know, right, it could be that those mathematical theories are, in some sense, one of those interpretations is the preferred one. But I didn't commit myself to which one is the preferred.
No, but that's where I'm heading, of course. The next question is then, does mathematics refer to an external reality?
Yes, I think it does. And what I think they are is basically patterns in nature.
Okay.
Patterns that are possibly connected with consciousness.
Okay.
Because when mathematicians so here's the idea. In order for a piece of language to be meaningful, it's got to be used in a systematic manner by multiple people. If there's not a systematic usage, then as Wittgenstein told us, there's no meaning there, right? If it's a random usage, that couldn't be meaningful. So when mathematicians all agree on some axioms and they set up a community, there's a pattern that emerges of speech, a pattern of language. And what I've given you is a way of abstracting out objects from the subsentential patterns of the language that's shared by the community of mathematicians.
Okay, then my last question. The problem of Platonism is indeed, as you indicated, how does our mind get in touch with these transcendental objects or structures, or however you want to call them? Well, there is, of course, Balaguer's solution, the full-blooded Platonism. How do you feel about that?
Balaguer's full-blooded solution was published 2 years after Linsky and I published the very same theory. We called it principled Platonism in 1994. His book came out in 98. And he referenced it, but he didn't show the connections. The problem with so there's a difference though. So that comprehension principle I gave you is completely unrestricted. It's a plenitude principle. Balaguer's full-blooded Platonism is a plenitude principle. But the problem that Balaguer has is every object for him only has one dimension on which it has properties. So it's complete and determinate down to the last detail.
Okay.
So he can't tell you, does the null set of the Mello set theory denote the null set, an object such that the continuum hypothesis is true, or the continuum hypothesis is false? For Balaguer, both of those objects are in there. But he can't get you from the theory to one of those unique objects. Whereas, because we distinguish between two kinds of predications, the Zermelo set theory puts us to a unique object that only encodes the properties of Zermelo-Frankel set theory, and continuum hypothesis is not part of it.
Okay.
So there's a very big difference, yes.
Thank you.
They're
Lovely
theories,
talk.
yes. It's a good question. It's a good question, but people
Thank
don't
you so
know.
much.
Yeah.
Anyone more?
Christoph? Oh, I see.
Thank you very much for your thought-provoking talk. But your very first premise is based on semiotics, the theory of symbols. Am I right? Do you hear me?
I
No?
hear you, but I'm not sure I understand the question. I'm using symbols, yes.
The very first premise you started with. The very first premise that a symbol has a meaning that you have embedded in it, nothing more.
I think the symbol acquires meaning through a systematic usage in the language.
The semiotics says a symbol has no meaning except that the one you ascribe to it.
Okay, how do you ascribe meaning to it? By using it in a systematic way. Not random.
That's what you talked about, the community of mathematicians. They use in a systematic way. The second thing is you have used an expression, analytic truth. Is it a camouflage of logical truth?
Sorry, what was the...
You have used an expression in your talk.
Yes.
Analytic truth.
Analytic truth, yes.
Is it camouflage of a logical truth?
So typically, the logical truths form a subset of the analytic truths. That's the way most people use the term. For example, it's an analytic truth that all bachelors are unmarried. But that's not a logical truth because bachelor is not a typical logical term. So there's a class of analytic truths that aren't logical truths, but all logical truths are supposed to be some form of analytic truths because they are true in virtue of the meaning of the logical words, not just the meanings of the general words.
No, I think I do differ because any analytical truth has to play on the playground of its domain. The mathematics plays not in the real world. Russell has already said it. If all men are mortal and Socrates is a man, Socrates dies.
So I don't presuppose any model theory. In order to make your claim, you have to presuppose a lot of mathematics. Right. But that's precisely what's in question.
But analytical truth is different from logical truth, you say. But mathematics binds itself to a logical truth on the assumptions or axioms it had already made. It doesn't care whether Socrates is a man or not. If all men are mortal and Socrates is a man, yes. Socrates has to be immortal. Whether Socrates is a man or not, it's not its bother.
Absolutely. I certainly agree. I don't see any inconsistency there with that.
So there is no analytical truth in a mathematical system beyond a logical truth accepted by the mathematics.
Well, the only way which I used the analytic truths in my system was to say, here's an analytic truth. In ZF, the null set is a set. I took the axioms of ZF, put them under the scope of the theory operator in ZF, and that, I claim, is an analytic truth about what ZF is. Yeah.
I ask my students this question. Yeah. How many colors...
I think we should let somebody else, because we could go...
So, let me excuse. Any further questions we can discuss in personal discussion. Thank you so much. So, next for a while for the next schedule. And over to Shubham.
Okay, sounds like we don't have any more time.
Thank you so much. Thank you so much, Dr. Edward and Zalta. It was nice to have you on the dais. Thank you very much once again. Ladies and gentlemen, can you please put your hands together for Mr. Edward Zalta.